The recording is in progress. You can start.
Yeah. Okay. Sharing my screen, so I'll just make this full screen. Okay, so can you see my slides okay?
Yes.
Yeah, great. Yeah, I'll get started then. And yeah, thanks for the invitation to come and speak. It's nice to be able to give this talk. So thanks for inviting me. And yeah, as you said, I'll just start with a bit more of an introduction about myself, what my background is. So yeah, sorry, just moving around the layout a bit. Yeah, so yeah, I've just put the links to various profiles on social media and my website on the side. And so I'm currently finishing my PhD at the University of Oxford, where I've been doing research in the foundations of quantum information science. So this has been theoretical research with some experimental collaborations, looking at things like thermodynamics and paradoxes on to do with quantum mechanics. And then alongside that, I've done various work with the quantum computing industry. So a while ago, I did an internship with a quantum software company called Riverlane, where I made this Raspberry Pi quantum computing lab. You may have seen these Raspberry Pi computers, and it was a simulation of a quantum computing lab. And then more recently, I've been working with IBM Quantum, and I made this series of videos resolving quantum paradoxes using quantum computing, in particular the Qiskit programming language. So I'll talk more about all of about quantum computing properly later. I've also done various things to do with public engagement. So there was a 3-minute video competition for high school students. Their videos are all on YouTube now, to do with quantum science and technology, if you're interested. And I've written a paper about quantum thought experiments as an educational tool related to these videos. And I now do various things with YouTube. I recently started a Quantum Foundations podcast on my own personal YouTube channel. And I've written some articles for Physics World magazine as well. So that's the summary of my background. And so today's talk, I'm going to talk about quantum computing. And I think a nice way of explaining the state of quantum computing today and understanding the implications of this technology is to kind of work through the timeline of quantum computing and how it's progressed from where it originated from all the way to what's happening now, and then to what we should expect for the future. So I'm going to start by talking about the origins of quantum computing. So it kind of started with this idea of quantum mechanics having these strange properties. Then we figured out that it could be useful for some simulations, which I'll talk more about. And we found that some tasks need quantum computers to be done efficiently, and they could be done more efficiently than certain tasks could be done more efficiently on computers based on quantum mechanics than ones based on classical mechanics. And then we discovered that for certain problems, they can be much more efficient. And then I'll talk about the challenges we face with quantum computing. So there's a problem of noise that I'll talk about. There was a discovery that it could actually be overcome in theory. So this meant that we could, in principle, build quantum computers. And then we've got to the point now where our best classical computers are struggling to simulate what we've done with quantum computers as we've been building them. And we've done some experiments to show that we can overcome this problem of noise on a small scale as well. And so what we look for in the future is seeing quantum computers give an advantage over classical ones for a useful problem. That's not been done yet. That's something we're aiming to do. And also creating large-scale quantum computers that don't have this problem of noise that I'll talk about, and they're called fault-tolerant quantum computers. So don't worry if this doesn't make much sense right now. We'll revisit it at the end as we work through this timeline to understand quantum computing. So let's start at the beginning, the origins and how it works. So before we talk about quantum computing, we need to talk a bit about quantum mechanics. So quantum mechanics is the theory of how systems interact fundamentally. We know that we can't use classical mechanics to describe how particles work, for example. We need to use quantum mechanics. So this theory was developed and shown by experiment that everything has to behave quantum mechanically. But then there are some strange implications of this. So I'm going to just mention two of them. So one of them is demonstrated by the Schrödinger's cat thought experiment. So this is a thought experiment where when Schrödinger imagined a cat, so I have one with me here, imagined a cat in a box trapped with a radioactive atom and a vial of poison. So I've got that here. So what happens is this radioactive atom may or may not decay, and according to quantum mechanics, it can be in a superposition of having decayed and not decayed. Now, in the box, if it decays, it will cause the hammer to smash the poison and kill the cat. If it doesn't decay, then the cat will stay alive and it won't do anything to the poison. And if we describe everything in this box using quantum mechanics, then it implies that the cat actually joins in the superposition that this radioactive atom can be of being decayed and not decayed. The cat can also be in a superposition of being dead and alive. And so Owen Schrödinger said, okay, this sounds really weird, sounds a bit crazy, but that's what quantum mechanics says about what happens in the box. But so it seemed very strange, almost absurd. But so that's one of the consequences, is we have superposition in quantum mechanics. And another is that we have entanglement. So you can think of entanglement. So if you imagine two particles that are like quantum mechanics. Now, what we can do is make measurements on these particles and then look for correlations between them. And what we're used to seeing certain correlations between systems in the classical world, such as a pair of socks. If you have a pair of pink socks, then if you look at one of the socks and see that it's pink, then the other one will also be pink. And so you have these correlations between a pair of socks and between lots of things in the classical world. But for two quantum systems that are entangled, it turns out that they have correlations beyond what's allowed by classical physics. And so it seems that there's these overall properties of the particles that goes beyond what we usually see in the classical world. And so this also is one of these interesting features of quantum mechanics. So we have superposition and entanglement. Now, how do we get to quantum computing from quantum mechanics? Well, there's two kind of origin stories of how the idea to do quantum computing came about. One of them comes from Richard Feynman. So during a lecture, he kind of presented this idea that, okay, we know quantum mechanics is what we need to use to describe how particles interact on a chemical level. To understand chemistry, we need to use quantum mechanics. So surely actually building our computer based on quantum systems be the best way to simulate quantum systems rather than trying to use normal classical computers to simulate these quantum processes? Wouldn't a quantum system be better at simulating that? So he kind of suggested this this idea. that quantum systems could be the best hardware for simulating quantum systems. And there's a different way of coming to quantum computing was later on by David Deutsch, who was trying to think of ways to test out what happens in this Schrödinger's cat experiment, essentially. So we have this, there's a controversy about what happens in the Schrödinger's cat experiment, because some people would say when you, that when the atom has either decayed or not decayed, and then causes the cat to be alive or dead, that the cat actually collapses into being alive or dead irreversibly. It's not actually alive and dead at the same time, it's just either alive or dead. So that's what some people think. Other people think that cat really is in a superposition of being alive and dead, and this is known as the kind of many worlds view of quantum mechanics. Whereas the idea that the cat's observation of the atom collapses it into alive or dead is more like the Copenhagen view of quantum mechanics. So there's these different interpretations. And David Deutsch was trying to think about how can we experimentally distinguish between them? Because lots of people would say, oh, it doesn't matter. This is just a philosophical question. The same thing happens both ways. It's not a science question. So he came up with a thought experiment to actually show that they do have different outcomes. And what he imagined was essentially trying to reverse the interaction of the cat with the atom. And then if you reverse it successfully, then that means that supports the many worlds view, that it was dead and alive. But if it doesn't reverse successfully, then that supports the view of an irreversible collapse from the Copenhagen interpretation. And how did this lead to quantum computing? Well, he was thinking, he thought it would be really difficult to do this experiment in real life to actually reverse a cat. It would be easier to reverse a simulation of a cat with the radioactive atom. And if we want to simulate this quantum process, we'd need to have our actual hardware being able to be in superpositions. So the hardware needs to be quantum. And so this was where the idea of a quantum computer came from, which then led him to post another paper after this one expressing the theory of quantum computing. So there are these two origins of the idea. And so now I'd like to explain a bit what quantum computing actually is. So what happened after people realized that we could process information using different hardware. So a key point is that classical computers work based on classical bits, which can be zeros or ones. So I like to think of these using a coin. You've got heads and tails, and as long as you have a system that can be in one of two states, like heads or tails, then it can be a bit, and you can use it to code your classical computer. Now, the difference with quantum systems is that when you have control over a quantum system, it behaves as a quantum bit. So that means it can be in the zero state. So I'm using a sphere to visualize this. So the top of the sphere is the zero state. The bottom of the sphere is the one state. And any other point on the sphere is a combination of 0 and 1, which is one of these superpositions that we've been talking about. So if it's on the side of the sphere, then that's like this superposition of the cat being dead and alive, but instead we're doing a superposition of 0 and 1. And then when you measure this qubit, you'll only ever see 0 or 1 as an outcome, but you'll see it with some probability, which depends on where it is on this sphere. So if it's closer to the 0, you'll have a higher probability of seeing 0. If it's closer to the 1, you'll have a higher probability of it being a 1 when you look at it. And when you observe it, you'll see that it essentially gets projected into either the 0 state or the 1 state. So it becomes that state when you do a measurement. And I like to think of it in terms of the coin that with the qubit, we don't just have heads and tails. We have heads at the top, tails at the bottom, but we also have this superposition state is like the coin spinning, because it's like the state where it's both sides at the same time. And so that's what having quantum control over a system lets us instantiate information using qubits instead of just bits. And what quantum computers do is quantum computers are built out of these qubits. And so so it's useful to think about what quantum computers are actually doing to these qubits. So we're used to classical bits where you can flip from 0 to 1 and 1 to 0. And you can do that with your qubit as well. You can apply something called a quantum gate, which flips it from 0 to 1, 1 to 0. But because we're working with qubits, not just bits, there's more gates we can do. One of them is called the Hadamard gate. And what this does is it takes your 0, your heads state, and puts it into this superposition of 0 and 1. So that's another gate you can do. And these single qubit gates are like rotations on this sphere, so you can understand them all using the sphere. Okay, so we've just looked at just having one qubit, but on an actual computer, we're going to have lots of these. So what can we do when we have lots of them? We can let them interact. So here we have another gate that we can do between two qubits, is called a control X gate. And what this will do is it'll actually create this entanglement that I talked about before. So if we have two qubits, then we can do this gate to let them interact, and then they'll become entangled, which means that they're correlated in this super strong way that's beyond what you can do with classical bits. So essentially quantum computers work by storing information in qubits and then manipulating that through these gates on these qubits. So that's the essential idea. But then what was quite exciting was when David Deutsch came up with this algorithm, which was the first algorithm which shows how a quantum computer could achieve something in less steps than a classical computer. Because if it turns out that we need the same amount of steps to do everything with classical computers, then what's the point of switching to them? So this was very exciting, and this algorithm was improved by Richard Josser, so it's the Deutsch-Josser algorithm. And we don't need to worry about the details right now, but I just wanted to give you the idea. So the idea is that we have this question we want to answer. So mathematically, the question is the function fx constant or balanced? I'm not going to go through what that means. We don't need to worry about that. The main point I want to get across is that using a classical computer, you would need to run an algorithm twice to figure out the answer. You need 2 steps. Whereas using a quantum computer, you can find out the answer with just 1 step. And this is a diagram showing the quantum circuit of how you implement it. So these are quantum gates that we saw before, the Hadamard that you saw, the H gate. And then a measurement is what this represents over here. But details of the circuit, but the point is that this circuit enables us to do something in 1 step that would take 2 with a classical computer. So this was very exciting because it shows that quantum computers can do some things in fewer steps than classical. Now, at this point, people thought, oh, okay, well, this is kind of neat, but, does it actually matter for anything? Is there going to be any useful problems where we get this speed up of quantum computers over classical ones? And that's when Shor's algorithm comes in. So Peter Shor came up with an algorithm for solving a problem much more efficiently with quantum computers than classical computers, and it's a very useful problem. So in particular, the problem is taking a large number and then splitting it into its prime factors. So this is a mathematical problem that's very difficult with a classical computer, it takes a very long time. And so usually it's easy to multiply the prime numbers to make the large number, but it's hard to factorize it back into those numbers with a classical computer. And this is the basis of a lot of our security online, is based on encryption that uses the fact that this reverse process is really difficult for our security, for online banking and lots of other online security. So then Peter Shaw comes along and says, actually, there's a quantum algorithm that could do this factorization process efficiently, much faster than a classical one. And if we were able to do that, then actually all of the encryption that our security is based on right now would be broken. It wouldn't work anymore. So this was actually, on the one hand, exciting because it shows that there's useful problems for which quantum computers are potentially much better than classical ones. So that got everyone excited. But it also got people maybe concerned that what if someone actually builds a quantum computer and then they can break all the cybersecurity that we've got? And so just to address the question of should we actually be worried that someone's doing this, it's actually, it turns out that the quantum computers that you'd need to implement this algorithm have to be really, really good. You need really big, really amazing quantum computers to be able to do this. And they're probably in the very far future, especially compared with the other applications for quantum computers that we're currently trying to work towards that I'll tell you more about later. So essentially, it seems that we don't need to worry about this right now because, as I'll explain, quantum computers are so difficult to build that making these amazing ones that can do this is in the very far future. But people are trying to prepare for that future by replacing encryption methods with ones that are robust to attacks from quantum computers as well as classical computers, and that's called post-quantum cryptography. So people are working towards this at the moment. So now I'll move on to explaining some of the challenges and progress in actually trying to build these computers. So how do we actually make a qubit? Because I've only described it on this abstract level of the zeros and ones. What about physically? How do I make one? There's lots of different ways of making them because essentially any system that you have enough quantum control over to get it into these two states and manipulate them, you can make a quantum computer out of. And there's various ways that that we can do that. One of them is, for example, using photons, single particles of light. We can use something called a beam splitter, which is like a half-silvered mirror, where if you send a photon in, then it will enter a superposition of going through and being reflected. And so you can create superpositions that way. So some people are trying to build quantum computers out of photons. We can use atoms. So if you imagine the electron in the atom being in different possible energy levels, you can use one of the energy levels as your 0, another one as the 1, and you can create superpositions of being in these energy levels and build quantum computers that way. So this is an ion trap one. So a single ion is visible here. This is from a lab in Oxford, which is very cool. And you can also build them out of superconductors. So yeah, you can use superconductors to also put them in different states using and then manipulate those. So this is the platform that big companies like IBM and Google are using to build quantum computers. And there's also lots of startups and lots of academic labs that are working on all of these implementations and other ones as well that I haven't mentioned. So there's lots of different implementations that people are working on. They have different pros and cons, different challenges to building them, to scaling them up. And there's a very, no one really knows what will turn out to be the best way of building qubits in the end. It might be that different ways end up being better for different applications, but at the moment, everyone's trying to pursue all the promising ones as much as possible. So why is it so difficult to build a quantum computer? Well, the problem is that this quantum state on the sphere is very fragile. So if I've got this superposition state, ideally, I want to let all my qubits interact and then measure them at the end, see what the outcomes are. But they're constantly being interacted with by the environment, with things out of my control. And if something comes in from the environment, some particle out of my control comes in, interacts with the qubit, then it's going to do a measurement and put it into the 0 state or the 1 state with some probability. So it's going to destroy my superposition state, and then I'm not going to get the nice outcome that I want, because I won't have had the nice interaction between the qubits, because they'll all have become either 0 or 1. So we have this very fragile state of the qubits that have interacted that we want to maintain, but we're constantly getting hit with this random hits from the environment, which we call noise, and that flips each qubit into be either in the 0 or 1 state and destroys this nice state that we want to manipulate, that's doing the work of this computation for us. So that's the challenge, is that we have noise constantly trying to attack our qubits. And so some people, quantum computing, thought that this would be that the noise would mean that we can never build a useful quantum computer. And the reason for this is that they said, as we add more and more qubits, we're going to get more and more noise. And so we're going to be fundamentally limited as to how good the computer can be. And so it will never reach the stage where it's useful, because we're just going to get more noise the bigger we make it. And then people discovered that there's a way we can actually correct for the errors. And this is called quantum error correction. So hopefully you can figure out what this heading says. You may have noticed that there are some typos. And in the process of looking at these words and figuring out that it says quantum error correction, you have done some error correction yourself. What you have done is that this must be the word quantum, this must be the word error, even though there were some typos that have switched the letters around. And we can do a similar thing of error correction with the qubits. So here, we use one letter for each word. We have a bunch of letters for each word. And that's what means that you can switch some letters around and you can still see what the word is. So we do a similar thing with qubits. We take our noisy qubits that we want, and we want to protect these qubits. So what we do is we bring a load of other qubits in, and we spread out the information from the data that we want. We spread it out onto all of these qubits. So that's like going from just having one letter to a whole word. And we call these logical qubits because it's the same data as before. We just have 2 qubits of data, but now it's physically spread out over a bunch of qubits. And then we do a very sneaky trick where we measure the qubits for errors without measuring what the data is, and then we correct those errors. So it's very surprising that we can actually do measurements on the qubits that tell us what errors have happened without destroying the qubit state. But it turns out that we can do this. So this was a big breakthrough when this was discovered, that we can do this. And so what we have to do is keep doing this measurement, the correction, apply our quantum gates on the data, and eventually we measure our data at the end, and hopefully we've managed to correct all the errors. And ideally, what we need is our quantum computer to not just do quantum error correction, but to be fault tolerant, which means that as you increase the size of your computer and add more qubits, the actual errors get smaller as you make your computer bigger. So it was shown that it's possible to make fault-tolerant quantum computers if we make the errors on the physical qubits low enough. So now in the industry and in academic labs, everyone's trying to make their physical error to be as small as possible so that we can get this fault tolerancy when we have lots of qubits. So we have a strategy for building good quantum computers in the future and overcoming the noise problem. But this is a very expensive process, expensive in the sense of we need lots of extra qubits in order to do this process. So instead of just needing 2 data qubits, instead of just needing 2 physical qubits for 2 data qubits, we need loads of physical qubits to do 2 data qubits. So this is going to need some really big quantum computers, which is very challenging to build. So I've discussed some of the problems and why it seems realistic to build quantum computers. But what are we going to do with them if we manage to build them? What's the potential for these machines? So there's various possible applications. There's the one that Richard Feynman was hinting at originally of simulating chemicals using a quantum system. So many people are looking into chemical simulation. This could help with pharmaceutical companies with drug discovery by making simulations of molecules much faster during drug development to create new medicines, for example. It could also contribute to designing fertilizers, which again becomes a problem of chemistry and simulating chemicals. And similarly, there are various applications to material science. For example, it may help with simulations that lead to designing new batteries that are more efficient. So they're all the ones that are kind of, well, there are a few that are more chemistry inspired. There's other potential applications as well. There's a field of quantum machine learning where people are looking into whether quantum computers could speed up parts of the process of training a machine learning algorithm or other parts of the machine learning process. There's people looking into speeding up optimization processes, optimization algorithms with quantum computing, and looking into financial modeling, seeing if we can get a speed up in those algorithms. And just some comments on what you might see and hear about quantum computing. There's lots of potential applications in a really wide range of industries, and it's really cool that they have all these potential applications. But something to look out for is there's a lot of hype around quantum computing, and sometimes this leads to certain publications or promotions saying things about quantum computers that are very hyperbolic and might not really reflect what they'll actually do. So if you see claims that they will cure cancer or solve climate change, that's not something that will happen anytime soon unless we have some rapid new breakthroughs. It's more of a far future thing, and maybe they could help with some aspect of some of these problems at some point, but they're not gonna just solve these problems in the near future. So it is something to look out for, is that many claims about quantum computers can be very hyperbolic, so look out for that. On the other side, a reason to be very excited about these potential applications is that even just a speed up in one of these things could be revolutionary in terms of changing the world, having a very large impact. For example, even if the only thing quantum computers did was help with designing better fertilizers, if that helps the food production in the world, then it'll be a very world-changing impact. So there's currently research being done in all these areas. And I just wanted to mention some of the long-term aspects as well. So the ones I mentioned before are the more, I guess, what we're working towards in the near term is trying to create these quantum computers for these applications first. In the long term, if we had these really good quantum computers, then it would actually be able to break the encryption problems that I mentioned. So hopefully we've switched to post-quantum encryption by that point. Maybe we could actually run this test that David Deutsch was imagining of trying to have an observer measuring a qubit and then trying to reverse that measurement. For that, we'd first need to have some theory of how we could actually simulate an observer on a computer, which we don't have yet. So that's why this is a very long-term idea, but we could definitely do more and more complex simulations and try and reverse measurements and see how that works. And I think, as we've seen with classical computing and with technology in general in history, is that there will probably be many unexpected applications that we don't know yet. So one of the exciting things is just to see what applications we end up discovering in the future as our quantum computers get better and we start playing with them more and using them. So I think there's lots to come in this mysterious aspect of human innovation using this technology. So some aspects of the quantum landscape at the moment is right now we have noisy quantum computers. So we've using the various platforms I mentioned, we have quantum computers with a few qubits. They range from the tens to even 1,000, but they're all noisy. So that's the difficulty there. But we do actually have quantum computers right now. We've reached a stage where quantum computers can do certain computations that are faster than a classical computer, although this is always a kind of moving target because classical computing keeps getting better. So then the quantum computing needs to keep getting better to stay ahead of it. And so this is a kind of constantly moving target, but we have reached that stage. We have had initial demonstrations of the quantum error correction that I mentioned, and fault tolerance, showing that adding more qubits will keep the errors low. So various different implementations have shown different aspects of this error correction process. And the timescale for the computers to become useful is honestly very unknown right now. So you'll hear some people say in 3 years they'll have done a useful application. Others will have a much more long-term view. They'll think we need the fault-tolerant ones, which are going to take a very long time to get them good, and that will take a lot longer. So there's a whole range of predictions about how long it will take, and ultimately no one knows. So at the moment, there's a kind of global race where you have universities, governments, tech giants, startups, and they're all working on different approaches on different aspects of quantum computing, working together, collaborating, competing, trying to build useful quantum computers. And so you'll hear these terms like NISQ is these noisy current scale quantum computers, and there's fault tolerant is these ones that use the quantum error correction. So there's these two different types. Another aspect of the quantum landscape is you've got people working across the quantum computing stack. You've got people working on software, hardware, the control systems in between, and this error correction theory and coding it and everything. And then you've got people working more on the applications side, trying to do case studies with the people in who would use these computers, trying to do benchmarking to see how we can quantify how good a computer is, and these milestone experiments like showing that quantum is faster than classical at a particular problem, or showing certain aspects of quantum error correction So these are the kinds of things that you might hear announcements about in the media, for example. So outlook on the future, hopefully we'll see the first useful applications in the coming years. That's the race is to the first useful applications at the moment. That's kind of what everyone's trying to get towards. Various organizations have published their roadmaps for quantum computing. And so they've been very explicit in what they want to do each year. So we will test those roadmaps as we move through the years. In terms of the workforce, they'll probably need more specialist engineers for the hardware, technicians, software developers. And in the coming years, we'll probably need to develop the algorithms, the noise reduction, the hardware, all kind of together to get the most out of the hardware as possible. So that's something people will be doing. And as I said before, there'll be lots of surprises as well. It's a very fast moving field, and results sometimes come out where it surprises everyone as to what kind of progress has happened or how things are going. So I'm sure we'll see those as well. So just to summarize before we pause for some questions, we've seen that the ideas of quantum mechanics, there's Schrödinger's cat, superposition, and entanglement, are these strange aspects of quantum mechanics. That leads to the idea of quantum computers, with quantum systems being good at simulating quantum systems and also testing this new world of quantum mechanics. We had the Deutsch-Jozsa algorithm was the first quantum algorithm that does something with fewer steps than the classical one. And then we have Shor's algorithm was the first useful one that does something a lot faster with quantum than with classical. Then we had the theory of quantum error correction, showed us that that building quantum computers and overcoming the noise problem is actually realistic. Then the first quantum computers were built based on these various systems. They now can outperform some classical algorithms for useless problems, but still outperform. And we've reached the level where we have some platforms have over 1,000 physical qubits, and some other platforms have implemented the initial demonstrations of error correction. Future outlook is aiming towards useful quantum advantage and ultimately in the long term trying to build fault-tolerant quantum computers. So I hope that was interesting. Happy to take any questions now, and I've also put a list of various resources that might be interesting if you want to find out even more about quantum computing. So yeah, thanks for listening.
Yeah, so thank you very much, Maria. Very insightful, thoughtful, grounded, and to the point. My request from the audience, you can ask your question in the chat. You can even come off on the mic and you can ask directly from Maria. But Maria, my first question is regarding the basics of quantum mechanics. So as we know, there are many interpretations of quantum mechanics, the Copenhagen interpretation, the many world interpretation. There are so many. Which one is your favorite and why?
Nice question. My favorite is the many worlds interpretation. So that's because when we apply, so essentially the logic is saying that if you apply quantum mechanics, let's say, if quantum mechanics applies to the particles that make everything up, then it should also apply to large objects. So this cat is made of atoms and particles, and I know that I have to describe them using quantum mechanics. So I should describe the entire cat using quantum mechanics. And then what we find when we do this mathematically, we describe the whole cat using quantum mechanics, and then we go, well, that means the cat also behaves in this quantum way that it could be in a superposition of different states if I had enough control over it. And so it's just a very nice, consistent way to understand quantum mechanics is that it applies on all scales. And then where we get many worlds coming out is this kind of natural consequence of, if you're saying the cat is in a superposition of alive and dead, then what that leads to is these emergent worlds where, so you're just interpreting the superposition as emergent branches of the world where one sees the cat dead and one sees it alive. So yeah, I think it solves lots of problems and it's very satisfying interpretation of quantum mechanics.
Yeah. So the next question is again the basics of quantum mechanics. Like in the year 1935, Albert Einstein with his two colleagues, Boris Podolsky and Nathan Rosen, has written the EPR paper, where it seems they agreed to the idea of quantum entanglement without accepting it. What's your take on it? How quantum entanglement violates the principle of locality, and to what extent do we think are you sure that what has been done on the Bell inequalities, the Clauser-Friedman test, and other people, they have won the Nobel Prize? Is there anything else, or it's settled for you?
So I think that we can actually save the principle of locality even with entanglement. And it's actually, I'm just gonna take the slides back to the very beginning. So this is a very subtle point because, yeah, if you hear popular science about locality, or even textbook explanations of entanglement, then often you'll hear this idea that when you have two entangled systems, when you do something to one of them, it instantly does something to the other one. And usually people say that Einstein was worried about this because it seems to violate the principles in relativity where nothing can travel faster than light, because if you do something to this and it instantly affects this, then something's happening faster than light, and that seems weird. Even though everyone agrees that you can't communicate using it, it still seems strange to even have these unobservable influences between entangled systems. And then people say, well, the violation of Bell inequalities with these Nobel Prize winning experiments that won the Nobel Prize a few years ago, that they prove that this influence is really happening. But it turns out that if we look at a particular description of quantum theory, essentially what we can do is save the principle of locality by shifting our understanding of what the physical meaning of each particle is. So part of that is accepting this universality of quantum mechanics that I mentioned before, of having it apply to all scales. And if you let quantum mechanics apply to your measurement device as you're measuring these entangled particles, and you really say that the whole thing is physically real, the whole superposition state, it doesn't collapse into just one of them, the whole thing stays as the physically real object. With this picture, you can keep locality and you can describe entanglement using a fully local way by shifting what you're saying is the real description of the object. So I'd be interested to have a conversation with Einstein today and the other authors of that paper and explain our current understanding of locality in this way and see if they're satisfied with that, because as far as I see, it satisfies the conditions that they wanted on entanglement, because you can get each particle having a complete description by itself, and you can explain entanglement that way by shifting your definition, your assumptions about what's real. So yeah, I'd be interested. As far as I see, we have a satisfying local explanation, although I will say that this is still debated in the community. Lots of people in the quantum information community don't see entanglement this way. They don't use this picture. And so that's why I made it the topic of my first episode on this Quantum Foundations podcast. So in this episode, I have a detailed discussion with my colleague Nisetu explaining these issues of locality in detail. So if anyone's interested, there is that as well.
Yeah, so there is a question from Majid. He's asking, what is the difference between physical qubits and logical qubits?
Yeah, good question. So let me skip back to the slide on those. So yeah, very good question. So we have physical qubits. You can imagine these implementations that I showed you before, where like the atom. So let's imagine that each qubit is encoded on a different atom. So we have an atom here and an atom here, and all of these are different atoms. And these two are containing our data, but all of these are each individually a different qubit. Now, to make logical qubits, what we do is we let these data qubits interact with all these extra qubits until we can essentially describe this whole set of 6 physical qubits. On an abstract level, it's the same as just having 2 of these data qubits. So, so what that means is that the data has been spread out. The 2 data qubits have been spread out over these 6 physical qubits. So abstractly, we can still treat them as 2 qubits on this abstract level. But on the physical level, we still have 6 physical qubits there. But they're all together encoding this data. So you can think of it as like encoding. So we take these 2 physical qubits, we encode that information across all these 6. And so now we have the 2 logical qubits encoded on these 6 physical ones.
Yeah,
so I hope that makes a bit more sense.
Yeah, so next question is from Sarfaraz. He's asking fundamentally about the practical applicability of quantum computers. Where do you see, as you mentioned, maybe in simulation, maybe in quantum sensing, maybe in quantum communication, where do you see the practical applicability? And follow-up question from me is, there was an announcement from Google in 2019 through the Singapore quantum computer, they claim that they have achieved the quantum supremacy. What does that mean? Can you please explain that? Was that anything practical, or just it was not that much practical? So I would be interested to have your point of view on that as well.
Yeah, the quantum supremacy experiment was nothing practical. It was a completely useless problem. But so that milestone was trying to reach the point of a quantum computer solving some problem faster than a classical computer. So it was not to do with it being useful at all. It has no practical application. And in fact, in that experiment, what they did is they really thought, okay, what's going to be something that quantum computers are really good at, that a classical computer will be really bad at, and let's try and do that, because that's how we can reach this milestone. So it really was kind of purposely designed to try and be good for quantum computers and bad for classical ones. So yeah, that quantum supremacy experiment was just trying to show that a quantum computer can do something faster than a classical one. The useful point is still in the future. That's what everyone's trying to race towards. And as I kind of alluded to before, we have this constant race with classical computing, because so getting quantum supremacy at some point in time doesn't mean you're going to keep it, because classical computing then gets better and is able to do that, solve that problem efficiently. And so the original Google experiment has now been simulated efficiently by classical computers, but then they've improved their hardware by that point. So they're still ahead of the classical. And so you kind of have this back and forth over time, both are getting better. And to the other question about when they'll be useful, or for what applications there'll be, or how close I'm just looking at the question in the chat, was how close we are to practical applications. So yeah, I think the first practical applications will come with probably the applications to chemistry. I think the quantum chemistry simulations, so maybe the ones that turn out to be useful for drug discovery or materials science. I think those aspects more likely to come first. And then there could be impacts on AI in terms of quantum machine learning. But from what I understand from the quantum machine learning field, I think we're going to need very good quantum computers to get an advantage in that field, potentially. Essentially, the difficulty is that with very large, good quantum computers, we can prove results about how good quantum compares to classical. It's much more difficult to prove results when we have smaller systems. So it's very difficult to actually prove whether a quantum computer will be faster than classical unless we actually try it. So there is a lot up in the air with the nearer term applications of how close the useful applications will be.
Hussein, please go ahead. Hussein, please.
Am I audible?
Yeah, you are audible. Please go ahead.
Hello, Maria. Hope you're doing great. First of all, it's a really interesting lecture, and thank you for sharing this information. I do have a question that integrates both quantum computing as well as AI in a sense that, let's say, first of all, I'll also tell you that I'm an AI engineer myself. So basically, in AI and in machine learning, we deal with complex calculations that even nowadays, as technology is advancing, even the high-end GPUs are also having a really hard time dealing with those calculations and complex algorithms. So correct me if I'm wrong, that quantum, by the arrival of quantum machine learning in AI or in these kinds of field, would they improve the process by just speeding up the process, or in terms of efficiency as well?
So do you mean efficiency?
By efficiency, I mean like
Efficiency in...
by efficiency, I mean like, would the models be even more powerful if we developed them using quantum computing instead of classical computers and the GPUs and stuff?
Mhm. Yeah, so I guess if it turns out that you can use your quantum computer to train your model faster, then maybe that enables people to train more powerful models that they couldn't do without. So it might it might be able to create more powerful machine learning algorithms in that way. Yeah. So currently people look at different parts of the machine learning process and ways that it could have various parts of that. So yeah, I guess it depends what combinations it ends up being
Okay.
useful for a speed up for.
Okay. Got it. Thank you, Maria. Thank you.
So, Maria, there is
Yeah,
another
thanks
question.
for the question.
So, Maria, can you take a few more questions, or you are running out of time?
I can take a few more questions.
Okay, so this would be, I think, the second last question. Someone is asking about Shor's algorithm. Can you please explain that algorithm? I think it's about integer factorization and how much logical or physical qubit you need to have. You need to have to run the Shor algorithm, and that would change everything. I think the quantum. This is the question pertaining to quantum cryptography. Correct me if I'm wrong.
Yeah, it is. Yeah, so there's a key part of Shor's algorithm is to do with finding its period finding, so finding these repeated patterns in a system. But It's quite a complicated algorithm. So rather than explaining how it works, I can recommend some videos. There's one, well, they kind of allude to aspects of how it works, explained by Shaw himself. So there's one, there's a couple on the Qiskit channel. One is called The Story of Shaw's Algorithm. It's a kind of cartoon version of 5-minute explanation about the story of Shaw's algorithm from Peter Shaw. And then there's a longer half-hour video on the Qiskit YouTube channel of Peter Shaw explaining the story of Shaw's algorithm straight from the source. So yeah, that might be the one that someone's linked in the chat. So yeah, there's that 5-minute one is a kind of cut down version of the 30-minute one. So they might be helpful for getting an idea of how the algorithm works. But yeah, at some point I'd maybe like to make a video about it or something, because I get this question a lot giving talks about quantum computing, and so it would be useful to have a nice actual explanation to refer to. But yeah, I won't attempt to do that now.
Yeah, so Maria, the last question is about these different hardware approaches. We have superconducting qubits, neutral atoms, trapped ions, photonic quantum computers. Where you are betting? Do you think either one of them would work or combination of them? What are the possibilities?
Yeah, I think I guess my personal opinion is that we should pursue any that seem promising until we hit some roadblock where it seems like it won't scale. It won't scale further and it won't end up being useful for useful applications. So we've seen this in the past, like for example, the first implementation of a quantum algorithm, there was a implementation of factorizing 15 with NMR qubits a long time ago. That was kind of an exciting first implementation, but NMR isn't a platform that scales with being used for quantum computing, so it's not been pursued for large-scale quantum computing. No one's trying to build large NMR quantum computers now. So I think that it'll be a case of pursuing all the different pathways that seem promising and then stopping if we have roadblocks. Otherwise, we keep going. And then maybe it turns out that one is the clear winner at the end, or maybe multiple platforms end up being useful. Maybe different ones end up lending themselves to solving different problems, but none of that is very predictable right now.
Thank you very much, Maria. It was wonderful to have you with our audience and means a lot to us. And we hope to get in touch with you for future events if you can find some time for our audience. So thank you very much and for this wonderful, wonderful session. And again, on behalf of the Aga Khan Education Board, I extend my utmost thanks to you for doing this with us. Thank you very much.
Yeah, thanks for inviting me and for all the questions. And yeah, thanks everyone for coming and for engaging with the talk. I see some people asking about the slides. I can send them to you afterwards. And yeah, is there somewhere where they can be pasted or something?
Yeah.
Or distributed. Yeah.
Thank you. Thank you once again. Thank you all the participants for your time and listening to Maria. It was a very nice, wonderful session. Maria, thank you very much. Take care.
Thanks. Bye.